3.3, reviewing solids, liquids, and gases. We've already heard about most of this stuff at least once or twice now, but we should know that matter exists in 3 states, the solid, liquid, gas, and their differences are influenced by variances in spacing and the motion of the molecules. So we're going to be looking at the particle model diagrams of solids, liquids, and gas. Identify properties of solids, liquids, and gases. Okay, we've already discussed this before, but one of the major concepts, fundamental characteristic of solids, liquids, and gas has to do with the distance between the particles. Okay, solids, the particles are typically pretty close together. Okay, but they're in fixed position held by strong intermolecular forces. The liquids have forces too, but they flip and turn, and so they have engaging attractive forces and repulsive forces as it flips and flows and so forth. And then the gases are really spread apart and they fill their container completely. Now, the states of matter, of course, operate on 2 antagonistic properties or entities, that one of them being the kinetic energy of the particles. Gases have the most kinetic energy, they're in constant random motion. Liquids have some kinetic energy because they're flipping and rotating, colliding, bumping into each other. And then the solids have kinetic energy, but that's only vibrational in place. Okay, remember that when matter has no energy, it would be at absolute zero, which would be 0 K, 0 Kelvin. The other property is the opposite here, which has to do with the strength of the interparticle attractions. Like a solid has strong particle attractions but lower kinetic energy. The gases, we assume, have no attractions, and they have the most kinetic energy, constant random motion, bouncing around the entire container. Of course, liquids would be in the middle, in between. All right, so going back just real quick, identifying the particle models, what you see is that the solid doesn't take the shape of the container, it contains its own shape here. The liquid does take the shape of the container at the bottom there, and then the gas would fill the container completely, as you can see based off of that diagram. All right, here's another couple diagrams, but I do like the one that refers to the water here. There's 2 separate water examples. This one's a little bit better to see. This is your ice cube. And the way that the interparticle attractions, because water is a bent-shaped molecule, remember it has like the 105 or 104.5 degree angle, that it forms this like hexagonal shape when it freezes. That's when the, hydrogen bonding, which would be the predominant IMF holds it in place. Because it forms that hexagonal shape, there's space in between them. And that space in between them makes ice less dense than the actual liquid water, okay? And this is one of the rare occasions where you actually have the liquid be more dense than the solid. Solids are typically more dense, okay? So looking at that, you see that they have spaces in here because it forms that hexagonal shape, whereas the liquid, they can jam pack closer together because they flip and turn and engage in attractive and repulsive forces as they're flowing, whereas here, those IMFs make that have some more space. Of course, the gaseous version of water vapor would be like any other gas, filling the container completely and all of that. 2 types of solids: crystalline, where they're in a pattern arrangement, some kind of 3-dimensional structure. It could be a lattice, could be basically a lattice structure, I would say, the best way to define that. This is going to be for your metallic stuff, your alloys, your ionic solids, and your covalent network solids that form the, crystalline pattern here. Although the ice one also, the way the IMFs engaged, made it in a crystalline pattern of the hexagonal shape too. Amorphous would be more randomized, you can see, where it doesn't follow a pattern and it's disorderly. So this is the best example between the two because these are both silicon dioxide. Quartz versus glass, okay? quartz being the crystalline part, covalent network, silicon dioxide, and glass being the one that's amorphous version of that. Now, in both cases, the motion of the individual particles is limited. So the only thing in the solid is going to be vibrational motion. The structure of the solid is influenced by strong interparticle attractions and the ability of the particles to pack together. So these interparticle attractions, in this particular case, we're talking about silicon dioxide, those are covalent network attractions. As opposed to in ice, we would identify them as intermolecular forces, with hydrogen bonding being the predominant one. So that's why we call it interparticle attractions here, is because we're grouping together the intermolecular forces with the intra forces as to how, you know, these solids are going to build. Of course, the intra forces, like covalent network, very much so stronger than anything that would be intermolecular, like the hydrogen bonding in ice. All right, liquids. Constituent particles in liquids are in close contact with each other. They are continually moving and colliding. The arrangement and movement of the liquid particles are influenced by the nature and strength of the forces between them. So stronger forces will make them more viscous, where they don't pour as easily, they have more friction and things like that. Okay? And the ones that have low viscosity obviously flow very easily, so their attractive forces and repulsive forces, you know, engage as they flip and move pretty easily. The solid and liquid phases for a particular substance are typically have similar molar volume. We say similar in the fact that because the particles of a solid and liquid are very close together, they're packed together, their volumes should remain pretty similar in the way that the molecules are packed. Now, like I said, in terms of density, liquids are typically less dense than their solid forms. However, there is the exceptional case, like with water. Ice is less dense than liquid water. Particles are in close contact at all times, so we would say for solids and liquids that they are incompressible or not compressible. Whereas gases, because they have lots of space, you can compress them, you can decrease their volume of their container, and then that will, of course, increase pressure, but you can still compress it. Gases. The gas phase, the particles are in constant motion, and we would say constant random motion. Frequencies of collision, the average spacing between them, are dependent on temperature, pressure, and volume. Because of this constant motion and minimal effects of forces between particles, a gas has neither definite volume nor a definite shape. So we would say it takes the shape, it doesn't take the shape of the container, it actually fills the container completely. So you go with it, fills the container completely. And it starts bouncing off the walls of the container, dispersing around, and of course the hitting the walls of the container is what creates the pressure, okay? And the more times it collides with the walls of the container, the more pressure you're going to have. Now, pressure can be affected by volumes and temperature. You can also increase the pressure of a gas if you add more gas particles there too, because then there'll be more of them to hit the walls of the container. The kinetic molecular theory, or KMT, assumes there are no interparticle forces between gases. Okay, we're talking attractive or repulsive forces. And we will cover the gases in more detail with the gas laws review that will be coming. We'll also be talking about the kinetic molecular theory and also ideal gas law, and then those that when the conditions when gases will deviate from ideal gas law or ideal conditions. That is going to be in a later unit, so we will cover that in detail in a later unit. Okay, so these three things that affect the different different spacing in the gases. Temperature, an increase in temperature increases particle speeds and causes the particles to spread out. Okay, so if it has like a balloon or a piston where the volume is not rigid and you can move it so that it increases its volume. If you increase the temperature, it will increase the volume and the particles will move faster. If the volume is rigid where it cannot move, if you increase the temperature, you increase the pressure, because then the particles will be hitting the walls of the container more often. Okay, and that's what this diagram is kind of showing you. Different cases here. Temperature increased, volume is constant, you increase the pressure. The volume is decreased, the wall area decreased, the pressure increase. Assuming temperature is remaining constant in the middle picture here, we're assuming that temperature is remaining constant. And then over here, container pressure constant, more gas molecules are added. That is, of course, is going to increase the volume. It allows for the piston to move so that the pressure can be maintained and stay constant. Assuming too, if you're just adding more gas particles here, this is Avogadro's law, the temperature is also remaining constant. Okay. So this is a nice chart that summarizes the different characteristics of solids, liquids, and gases. We have gas assumes both the volume and shape of its container. The liquid assumes the shape of the portion the container it occupies. Like you pour water in a cup, it's going to take the shape of the bottom of the cup, or however high you pour it. And then for the solid, it retains its own shape and volume. Expands to fill the container. We say that for a gas, fills the container completely. The liquid will not expand. It will just take the shape of the portion of the container it's in. And then, of course, solid doesn't take any shape. It has its own shape. Okay, so here's compressible. We would say liquid is virtually incompressible, and the solid too is virtually incompressible. And down here at the bottom, it talks about diffusion and the flow. You can see those there, makes sense. But do remember that solid particles vibrate in place, so they do have kinetic energy. And if you increase the temperature, you increase the vibrational motion until eventually you get to that melting point and then it starts to overcome some of the forces. All right, so a couple of little problems like here. Nice, easy multiple choice here. Of the following, the best explanation for the fact that most gases are easily compressed is that molecules in a gas. Yes? RB, relatively far apart. I would go with that too. If they're far spaces, you can squish their space a little bit and compress them. So that would be correct. And the only way to answer this question is to know the different characteristics of the gas and the spacing. Here is a drawing one. Okay? So, carbon tetrachloride, as you see, we like to use this for examples. Liquid has an L next to it. In a previously evacuated container at 30 degrees, that means all the other gases have been vacuumed out of the container. That's what it says by evacuated. So the only thing in there is going to be the carbon tetrachloride liquid. Okay? And some of that liquid evaporates. So in the box below, draw a particulate diagram to show the species in the container after some of the liquid has evaporated. And it gives you, a key to use in order to draw this. So go ahead and take a moment to draw that. We'll come back in just a minute. All right, it says we have the carbon tetrachloride liquid and it's going to evaporate. So what kind of change is that?
It's a physical change from going from a liquid to a gas. A physical change, any phase change is a physical change. So we're still going to have it be carbon tetrachloride. It's just one is going to have the properties of liquid and one is going to have the properties of gas.
Correct. So, because this is evaporation, which the liquid is evaporating into the gas, you shouldn't be breaking it up into any of the individual ones like these. They're all here as distractors. Because this is a phase change, the carbon tetrachloride molecules stay intact. The only thing that's being overcome are those interparticle attractions. And in this case, it happens to be London dispersion forces. Okay? So, yes, you should be drawing the liquid at the bottom, but is the liquid at the bottom going to be like a regular pattern, or should it be pretty random?
Really random.
Should be random since it's a liquid, and then you should have a few gas particles that have detached. So this is what I have here, as you can see, some liquid particles at the bottom, and the gas has, you know, evaporated. You see a couple random ones there. All right, so, and they probably would give you that point to show that you have the layer random at the bottom, and then you have a few that are separated, filling up the container in random spaces. The last problem I have here for drawing and solids, liquids, and gases, we have molten iron versus solid iron. What does molten iron indicate to you? It is melted. It is now a liquid versus solid iron. And then they give you two data points here. We have the molten iron, 6.98 grams per milliliter density, and the solid iron, 7.874 grams per milliliter. So, now you have to recreate these drawings based off of those densities and accounting for them. So go ahead and take a moment to do that. Be very careful about your spacing, the way that you draw your iron. Now, when you draw your iron, should it be one circle or two circles? One circle, because iron's not diatomic, it is monatomic, so you would draw them as single circle atoms. Which one is less dense, the molten or the solid? Molten is less dense, so that means it should have more spaces, and it's still a liquid, so they should be kind of randomized, as opposed to the solid, which should be fixed position, less spaces. Because remember, density is a measure of the matter in the amount of volume it is. So the one with is more dense has more packed particles in the given volume. So it should look something sort of like this, where you have, I did 10 circles, so they're right next to each other in the solid. Over here in the molten, I kind of drew myself a container to show that it's in the container. But you can see there's a little bit more space between them, and they are more randomized. Okay? They shouldn't be over all the entire space, because then you would be indicating it's a gas. It should be still pretty packed together, but randomized at the bottom. Okay? And a little bit more spaced out. So that's why I drew my own separate little container, showing that it's taking up more space for those 10 particles, whereas in the solid, they're closer together. Okay, so that's just one representation you can use as an idea. Remember, with solids, liquids, gases, the spacing of the particles are going to be, you know, something that you need to really take into account. And also watch for those physical changes, so you do not break them up into chemical reactions into individual atoms and or new stuff. Okay, phase changes, remember, just indicate that same individual particle.